we need some linear algebra initially to generate examples of groups, which are the first topic of the course. And the linear algebra we're going to need all concerns the set of all n by n matrices, where n and n is the same number, so square matrices. Now, the entries of the matrix, if you're in the ith row and you're in the jth column, the entry would be aij. That'll be the notation I'll use. So the first row looks like a11, a12, up to a1n. And then we have an1 down here, all the way over to ann. I'm going to take the entries all just to be real numbers. And the set of all n by n matrices I'm going to denote MNR. So that's all collections of n by n matrices. So those of you who've studied linear algebra know that that's a vector space over the real numbers. It has dimension n squared because you have a basis for that vector space of the matrices that have zeros everywhere but a 1 in the ith, jth place. So in particular, as a vector space, you can do a number of things in this set. For example, you can add matrices, A plus B. So if you have a matrix where the entries are aij, and you have a matrix where the entries are bij, then the sum of these two matrices has entries aij plus bij. So you just add the elements in the ijth place. That's the addition law in the vector space of n by n matrices. And you can also multiply matrices by a real scalar. If you have a real number alpha, and you have an n by n matrix aij, then you can multiply alpha times a and get the matrix where the entries are alpha times aij. And then we multiply every member by alpha. That's the scalar multiplication in the vector space. So that's what makes this a real vector space of dimension n squared. As I say, you have to write down a basis. That's not difficult. Now, what's unusual, that would be true for n by m matrices too. You can add them, you can multiply them by scalars, and the dimension is m times n. What's unusual about n by n matrices is not just that you can add them or multiply them by scalars, but that you can multiply them, which is a fairly complicated operation. Namely, if you have two matrices A and B, you can define a new matrix A times B. So those of you who've studied this since 10th grade know that if this has entries Cij, then you get the ijth entry of Cij in the following manner. You go across the ith column of A, ith row of A. You go down the jth column of B. You multiply this element by this element. Then you multiply this element by this element and add those. You multiply and you add up. So the formula in mathematics, although it's not that useful, is the sum over k of aik times bkj. And you might wonder, what the heck does that mean? But it certainly defines, given two n by n matrices, a third. The matrix multiplication. Now, when you study linear algebra right, and we will review linear algebra done right, you get a little bit away, you step back from the theory of matrices, and you see what matrices represent. And what matrices represent are linear operators. So in particular, this is the set of linear operators from an n-dimensional real vector space to itself. Every matrix is a way of writing down a specific linear transformation. We'll do that later on, but it's a good thing to bear in mind. Because if you understand that a matrix represents a linear transformation, then what multiplication of matrices represents is the composition of transformations. That's not obvious from this formula at all. You have to unwind a million things to see that. So if A represents the transformation of T from Rn to Rn, and B represents the let's see, I'll do B first and A second. And B represents a transformation S from Rn to Rn, represented by B. And remind yourself how this works. And that's done in Art and 2. Then the product, first do B, then do A, represents the composition of the transformations First, take the transformation S and compose it with the transformation T. Now, one thing that we emphasize a lot when you study linear algebra is that that may not be equal to first doing the transformation T and then doing the transformation S. So remember, and this is really important, that it is true that if you add A to B, it's the same as B to A. That's just the commutativity of the laws of addition, because matrix addition just takes place coordinate by coordinate. But it is not necessarily true that A times B is equal to B times A. There are examples where this is not equal. So the only way to really convince you of that is to write down a specific example. So I will write down a specific example for you, which Artin uses. If you multiply this matrix, you have to go to 2 by 2 matrices, because multiplication of 1 by 1 matrices is just multiplication of real numbers. Right? I mean, if n is, this is k, it goes from 1 to n. So if n is equal to 1, this is just, you get this matrix by taking the product of the entry in A by the product of the entry in B, and multiplication of real numbers is commutative. But if you go to 2 by 2 matrices, it's no longer the case. So for example, if you multiply this matrix by this matrix, you'll find that the only non-zero entry you get is when you go across this row and down this column, right? So that would be an entry up here. And all the other entries you find to be 0. Let's try it in the other direction, see if I got this right. This would be typical, where I work this example out wrong. So that's this matrix here. Then this one goes up here. Are there any places where we get a non-zero entry here? This is 0. This is 0. This is 0. And this is 0. So this turns out to be the 0 matrix. So this is the product of A and B. This is the product of B and A. These matrices are clearly different. By the way, this matrix I'll just call the 0 matrix. It's the 0 element of the vector space. It's whatever, it's the element of the vector space such that when you add it to an arbitrary vector, you get the vector back, because you're not changing anything. The matrix that looks like this, 1, 1, 1, 1, 1, all down the diagonal and 0 elsewhere, I'll call that the identity matrix. That's a distinguished matrix. And that has the property, if you work out this addition, this multiplication law, that if you multiply anything by the identity matrix, you get it back. So I'm running out of room here. Let's go here. So 0 plus A is equal to A plus 0 is equal to A. And no matter which side you multiply by the identity matrix, sorry, is I times A. Sorry, this is, yeah, this is A. If you add 0, and if you multiply by I, you get A. So you have a multiplicative identity and an additive identity. OK, some other laws of matrix multiplication and addition. For example, you have the distributive law and you have the associative law. So the distributive law says if you multiply A times B plus C, it's the same as multiplying A by B and then adding the product of A by C. And the associative law, which is the most important, is that if you multiply A times B times C, and you first multiply B times C and then times A, that's the same thing as multiplying A by B and then multiplying by C. So the normal laws of arithmetic, addition and multiplication all hold except for the commutativity of multiplication.